Hello everyone. In this video we are going to talk about the runtime of the code as well as anonymous or lambda functions. So getting the runtime of code is very easy in Python. You need to import the module time, and from there you need to run the method called time as well. So you can get the start time of your code by time.time. Then you can do whatever you want, and then at the end, again, you get the time.time, which is the end of the runtime. Subtract them and multiply it by 1,000 to get milliseconds. Okay? So this is going to be in seconds, but if you multiply by 1,000, you're going to get in milliseconds. And most of the time, that number is small, so you better show it in milliseconds, which is a little bit more a larger number. And here, for that, I have a 3x3 matrix, and I'm gonna raise that matrix to the powers, the increasing powers from basically 0 all the way to 999, right? So each time I multiply the matrix by itself and assign it back to it, and keeps doing that. And this is for a 3x3 matrix. Although not necessarily super computationally expensive, but when you do it 1,000 times, it is going to take a few milliseconds. And here I go ahead and run this part of the code for you. So you see that the runtime is about 3 milliseconds. And if I run it again, I'm not going to get the exact same number, okay? You see, it's close, but not perfectly. You see, it's about 7.007 of a millisecond different. If I run it again, I get this time like 0.09. The first time I did it, of course, a little bit smaller. And so if you really want to get, you see here it's much smaller. If you really want to get the runtime, you better run your code in a bunch of times and get the average of those. So if you want, really, what I suggest is to go ahead and create another for loop and run this operation in that for loop so many times, and then see the basically the average runtime in that for loop. So what I can do is, first of all, defining the matrix, since it's the same matrix, I can have it outside that for loop like this, and then say for JJ in range, and then say 100, and then what I need to do now is to bring all of these 4 lines one tab forward, so they are under my outer for loop like this. Okay, so I get my start, do the computations, get the end time, and then I go ahead and store this end minus a start times 1,000 as the JJ entry of some storage vector, and I can call it runtime vector JJ equals this. Okay, but you better start this vector ahead of time with a bunch of zeros, and then fill it instead of each time resizing it. So I say this is NP of zeros, and then I say, because you know the size, if I go from the range 100, you're going to start at 0, go to 99. So you're going to have 100 data. So it's going to be 101, okay? So you started at 100 and 100 by 1, 0 runtimes, and then inside this JJ loop, you're gonna fill those entries. And when you want to show this, you say runtime vector dot mean, and get the average and show it in milliseconds. This way, you are going to get what? A lot more reliable time instead of running it each time and getting a different number. So let's go ahead and run it now. So here we ran the code, and you see this is the runtime after about 100 times. And this is way more reliable than all those random numbers that we did individually. So this is way more accurate. And the more you run it, you change this to a bigger number, 1,000 times, 10,000 times, that number is going to be more reliable because that shows the average of the distribution, not just a single random sample. Okay, the next part of the code that we are going to work on is going to be the anonymous functions or inline functions. And here you also call them lambda functions because they have this keyword lambda. So you give it a name, you pass it the input arguments, as many as they are, separated by a comma, then column, and then the criterion of the function, which is the same as output. So these functions, you can define them in a single line. They don't need def and definition, and they are shorter than any regular function that we learned in the previous video of mine. So you can pass to them a scalar for x, a scalar for y, and they return the value for you. Or you can pass to them an entire vector for x and an entire vector for y, and then it is going to pick pairs of numbers from x and y, right? As I show you, 3 and 5, 2 and negative 2, 1 and 0, and it's going to return an output vector. So whether you pass it a scalar or vector, this is going to work just fine. So here my function is xy squared plus 5xy plus 3. So let's go ahead and run that. And you see that for 1 and 2 it returns 17, which is right. It's 1 times 2 squared, which is 4, plus 1 times 1 times 2, which is 10, plus 3, which is 17. And then if you pass to it the pair of 1 and 0, of course you get 3. If you pass to it the pair of 2 and negative 2, you get negative 9, and 3 and 5, it will give you 153. So you can pass to it scalars or vectors, and it has no problem. It works just fine. One of the other places that you can use anonymous functions is you can pass an inline function as an input to a regular function. So let's say I have a regular function def, and then I call it my square, okay? And then I pass to it some f value, and this guy is going to return what for me? F squared, right? That's all this function does. Good. Now what I will do is I say print for me what? The f of what? Inline, f inline of 1 and 2. So instead of passing what? A number to this function, I pass the out value of this if inline to that function, and there is no problem. I can pass a function to this. Look here. Okay, so if is not defined. Of course not, because sorry, I have to say my square. And here, 289. Right? You know, 1 and 2, the output was 17, and if you square 17, the output is 289. So when is this any good? This is good when you want to optimize a function of a function, or a functional, basically. Right? In those cases, like optimization problems, finding minimum of some functions, right? Where this output function is your minimizer, right? Then this is going to be very useful, or for roots, or as I said, functionals and so on. So you can, let me add that for you, that you can pass an inline function as an input to a regular function. And here I can say you can pass vectors to an inline function as well. So you don't need to just pass a scalar to it. You can also pass a vector to it, okay? And here, just wanted to show you another point that might be interesting to you is I'm going to define a regular function which does the exact same thing as this inline function. And then I'm gonna do some heavy computations using one of them at a time. So first I do the computation using inline function, then I do it using regular function. And in both cases, I'm gonna get what? I'm gonna get the total runtime, and I'm gonna show the runtime. I had this line, I don't know what happened to it. Let me add it. And I'm gonna show the runtime. So the idea is an inline function faster than a regular function? Just because it's more brief, is that also necessarily taking less time to do a heavy computation like this? And what is this I'm doing? So I have a nested for loop, and the loops, one of them goes from 0 to 999, the other one goes from 0 to 1999, and each one with these many times, I am going to call these functions with some number I and j, and I assign the value to the output to this value variable, right? So for about 2 million times, I'm calling each one of these, and I get the total runtime in milliseconds. I want to see if that makes any difference. So let's go ahead and run this, and if you can see, the runtime of them for the inline function is about 1374 milliseconds. For the regular is even a little bit less, 1358. They are almost the same. So the idea of inline function is the ease of use and the fact that you can pass it to a regular function as an input, not the fact that it runs faster. Okay, so it's not really for the sake of a runtime that we use an inline function. Just wanted to emphasize this for you so you know that that's not why we use what? We use the inline functions. So hopefully this video is useful to you, and I will talk to you in my next video. Thank you.